Dear students, welcome to this talk on electrodynamics. It is little difficult to understand the basic principles of electrodynamics without having a thorough knowledge about the fundamentals of electrostatics and magnetostatics. So in this video, I would like to give you the basics of electrostatics, the basic equations and different topics. And in the next video, I would like to give the basics of magnetostatics. Okay, let us start with electrostatics.
We know that electrostatics is related to static charges and the associated static electric field. The static charge, we know that may be of different types. The most common type is a point charge. Usually we represent a point charge with the letter small q. We can see that around the point charge there is a region. Usually we identify a region around the point charge, and that region is defined as the region where some electrostatic effect is experiencing, and that is called the electrostatic field. The charge may be in the form of a collection of point charges also. A point charges like Q1, Q2, Q3, Q4, Q5, etc. So that the total charge Q may be represented as summation Qi. Another type of charge distribution is the line charge distribution. Here the line charge distribution is characterized in terms of the line charge linear charge density lambda coulomb per meter is considered a small length dl. Then the charge accumulated on that length is called lambda dl, so that the total charge is given by the expression q is equal to line integral lambda dl. Also surface charge density. The surface charge is characterized in terms of sigma, and the small surface element ds is considered ds, so that the total charge in this case is given by q is equal to a surface integral sigma ds. Then the most common type of or general type of charge distribution is that volume charge density, and the volume charge is represented in terms of the charge density rho, and the volume element dv or d tau. In some cases it is taken as d tau, and or in terms of the volume dv, so that the total charge in this case may be taken as q is equal to volume integral rho d tau. So different types of charge distributions produces electrostatic field around it. All these charges are static, so that the electric field produced in this case are stationary. And the static field, we know that it produces some effect on another charge placed in the region. In this picture, rho represents a point distribution, and around that there is a colored region, and in that region, if we place some other charge, there will be some force experiencing on that. In this case, it is taken as a positive charge, so that field lines are emerging out, and there is a boundary region, and outside the boundary region, if we consider any point, we can see that that is outside the field of repulsion or field of attraction associated with the source charge, so that is at infinity. So in this context, it is possible to represent the electrostatic problem as a cause-effect principle. So the cause is the source. In this case, it is the electrostatic charge, or the stationary charge is the cause, and the effect is the field, electrostatic field. And the field in this case is taken as E, or it also may be represented as D. In the case of a material medium, we have to represent it in terms of the electric flux density D. So the electric field distribution. So in the case of electrostatics, the electric field distribution is of much importance because the aim behind any electrostatic problem is to find the effect due to that cause. That cause may be a complicated one, maybe a simple charge, maybe a distribution of charges, maybe a distribution at a point charge. Whatever may be the case, it produces an effect at a particular location, and we want to identify the force acting or the effect or the field at the particular location. So that is the ultimate aim behind this any electrostatic problem. So the most important method to find the electric field, as I have mentioned, is based on Coulomb's law. We know that the Coulomb's law, in the case of Coulomb's law, there is a test charge, a source charge is there, and also we have a test charge, capital Q is there. Even though this test charge is represented as a capital Q, we can see that the magnitude of this test charge is very small, or the value of the test charge should be chosen to be very small, such that its presence is not at all affecting the field produced by the source charge. So if it is placed at a distance, say r, the force of interaction between this is given by Coulomb's law as F is equal to 1 by 4 pi epsilon 0 Q into capital Q divided by r square into r hat. That is the direction of the force acting. And the test charge should be very small. Its presence should not change the electric field produced by the source charge. And the force acting on a unit test charge, that is, if you place a small test charge and divide the force with that test charge, so that F divided by the magnitude of the test charge is called the electrostatic field at that point. That is, the force acting on unit test charge is taken as the electric field. So this is the most common method or the basic method to find the electric field or the effect due to the electrostatic cause, that is a stationary charge. Now in this case, in this equation, one more point is to be mentioned here, that is the value of a constant here. It is epsilon 0. Now the epsilon 0 is called the electrical constant. Now usually we take it as a constant associated with Coulomb's law, but this particular constant gives some information about the property of the medium to concentrate electric field through the region. The value of this constant is different for different media. For the free space, it is taken as epsilon 0, the value 8.850 or 854 into 10 raised to minus 12 farad per meter. In the case of a material medium, we will represent in terms of epsilon, and we will define another constant there as epsilon r, is called epsilon divided by epsilon 0, and this epsilon is called the dielectric constant or the relative permittivity of the medium. So that decides the field concentration inside the region, and we can see that microscopically it is related to a property of the medium called polarization. What happens when the material placed in an external medium as far as the field interaction with the molecules are concerned? There some polarization effects occurs, and that is represented in this equation as the permittivity of the medium epsilon. So we'll discuss more about permittivity in the coming sections. Now, the second important method to find the effect due to the electrostatic cause is called Gauss flux theorem. Now, Gauss flux theorem, the statement is well known. The total normal electric flux over any closed path is equal to 1 by epsilon 0 times the charge enclosed by the surface. Suppose we have any charge at some location, and we suppose the field distribution around And if you have any volume around it, and if you consider any surface with electric field passing over as E and the area as ds, then we can see that E dot ds is actually the electric field passing through the area element ds. E dot ds means the normal component of electric field over the element ds. And the surface integral, closed surface integral, E dot ds is equal to 1 by epsilon 0 times the charge enclosed by the surface. In this case, the charge is q. And if it is a distribution of charges, then instead of this q, we have to write it as volume integral rho theta. Okay, so the surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho theta. So it is very simple method to find the electric field due to a static charge distribution, and this is useful in some symmetric cases very much. So symmetric cases such as problems having a spherical symmetry, like that of a point charge, or that of a charged sphere or a dielectric charged sphere, etc. Or in the case of a cylindrical symmetry, cases with a cylindrical symmetry such as a line charge or a charged cylinder, or with some plane symmetry like the example of a capacitor, etc. So the symmetry means over certain region of surface the electric field is constant. The surface may be spherical in shape, cylindrical in shape, or plane in shape. In such cases, by making use of Gauss-Flux theorem, it is very easy to find the electric field without using the basic principle, Coulomb's law. So that is the importance of this equation. Now we have one more form for this equation, that is the point form or differential form of this particular equation, that is del dot E is equal to rho by epsilon 0. This is the differential form of this equation, that is the divergence of E is equal to the charge by epsilon 0, and this equation may also be represented in this case of a dielectric medium as del dot D is equal to rho S, or sometimes rho P, like that. Del dot D is equal to rho. So these two equations are mainly used to find the effect due to an electrostatic cause. Now another important point that is of much relevance in the case of electrostatics is something related to the property of the electrostatic field, that is, it is conservative. Now we know that in the case of conservative force field, the work done around a closed path is equal to 0. We are familiar with the gravitational field. Now it is conservative. That means if we move a mass around a closed path, the work done is equal to 0. Similarly, electrostatic field E is conservative, means if we move a charge around a closed path, the work done is equal to 0. That is related to the energy, the work associated with that particular movement is equal to 0. That is represented here as line integral E dot dl. E is actually a force, that is force on unit charge. E dot dl is a distance, so E dot ds is that of work. So line integral E dot dl is equal to 0, closed line integral. So if we have a point charge here, then a test charge placed at this location, and it is moved here and there, and finally it is again reached at the same position. Any distance is taken as a small distance dl, and the electric field corresponding to that point is taken as E. Then E dot dl is taken. Then we take the line integral, closed line integral E dot dl, and it is equal to 0. And this is called the conservative property of the field. And the point form or the differential form of this equation is given by del cross E is equal to 0. That is, curl E is equal to 0. That is electric field. The curl value of electric field del cross E is equal to 0. So E means electrostatic. It is not with the case of a time varying field or electromagnetic field. It's only applicable to static case. Del cross E is equal to 0. Then we have to discuss about two more vectors in this context, that is the two vectors, field vectors D and the polarization vector P. Now the field vector D, as I have mentioned just now and in the earlier slide, is that D usually represent in the case of a material medium. In the case of free space, we represent the effect in terms of the E vector, whereas inside a material medium, we are representing this in terms of the field density, flux density vector D, and its D is given by epsilon E. D equals epsilon times E, where epsilon is called the permittivity of that medium. And the most general form of that equation is given by D equals epsilon 0 E plus P. Epsilon 0 E plus P, where P is called the polarization vector and D is the electric flux density vector. That means when any material is placed, a dielectric material is placed in an external electric field E. External electric field E. What happens is, say this field, we can assume that a positive here and a negative here, since this is the direction of the field vector. And a positive here means a polarization, minus polarization accumulates here. If it is a homogeneous medium, only positive and negative at the ends, if it is of a regular shaped material. And if it is irregularly shaped and of anisotropic behavior, then the charge concentration will be inside also. So in this present context, we assume that there is only some polarization or charge distribution on the left side and on the right side, and this produces another field inside. So the net field inside changes. So the electric flux inside is represented as the electric flux density D, and the reason for the change with respect to E is the polarization vector P. Then again, coming to our problem of any electrostatic problem, that is to find the electric field, that is the effect due to the cause. We know that there is some complications in this particular procedure due to two reasons. And the first reason is related to the source. I have mentioned earlier that the source may be of different types, that is point charge, a collection of charges, or a line charge, surface charge, volume charge. And we are interested in evaluating the electric effect corresponding to a complicated charge. And we know that we are interested in evaluating a vector quantity. Electric field is a vector quantity. And the electric field measured or the produced at the point may be different due to different portions of the source, or different from different sources. The electric field may be different, and it shows different directions as well. So the net effect is the vector sum of the electric field due to different portions of the source. So the calculation, say we have the electric field measured, maybe a point charge here, then maybe a line charge here, maybe a distribution here. So this produces an electric field, say E1. Okay, then this line charge again produces an electric field that may be represented as E2. That itself is a combination, means we divide it into different regions, and from each region we have to find the electric field and take the total electric field. Similarly, in this case also we have to find a small region here and find the electric effect due to a small portion, then integrate over and total electric field measure, that is E3. So the calculation of electric field becomes a complicated procedure due to the complications of the source. In that case, we need the help of a situation, or in this situation we make use of the help of potential formulation. And the potential V, electric potential V, is a scalar quantity, and with the help of V we will tackle this problem. And the second is with respect to a medium change. The medium change is represented in terms of boundary conditions. That means, suppose we have a glass medium placed inside. In such a situation, we have to identify or find out what happens to the field when it crosses the boundary of the glass medium and so on. So before that, let us discuss a little more about the potential formulation. The potential at a point, say a source charge placed at this point, and we define a region around this, and outside the region, suppose a point is taken here. And if we take a test charge at this point, we can see that the force acting on the test charge is equal to 0 because it is outside, so it is at infinity. Now let's we take this test charge to any region here, any point here P. So we divide this into small regions and move it to, from this point to this point there is no work done. As we take this to from this point to this point, we have to do some work. And for any point, any small distance dl, the electric field E, so the work done is equal to E dot dl. So the work done in taking this test charge from infinity to the point P is given by line integral E dot dl, that is line integral from this infinity to P, that is this line integral from infinity to P, E dot dl, and that is measured as the potential corresponding to that point, usually represented as V, or sometimes it is taken as Vp, the potential at that point. So actually this is the definition of potential. Now we can consider 2 points, one point P here, another point Q here, R here. Then the potential between this point and this point, that is Vp and Vr, the difference can be taken, and that is taken as the changing potential dV is equal to Vp minus Vr. So this potential formulation helps us in simplifying the problems related to a complicated source, and we are also are able to represent this equation in three-dimensional form, or the point form, differential form, as E is equal to minus del V. That is, the dV is equal to a small change in potential. So we can convert that into three-dimensional form, and you will get this E as minus del V. So after evaluating the potential P, we are able to convert that potential into the electric field, and that is the procedure that we adopt. Now first find the potential, that is a scalar quantity. The complications associated with the source is of not much relevance in that case. Now after evaluating the potential, use this expression E is equal to minus del V and find the electric field. So that is the first simplifying tool. And the second simplifying tool is the boundary condition. I've just mentioned in the case of a dielectric contrast, we consider free space like this around the point charge Q, free region. There is no discontinuity. Everything is represented by the constant epsilon zero. In this case, the evaluation of the electric field at any point is very simple, but instead suppose one dielectric medium is placed or present here, and its property is taken as epsilon. So what happens? The electric field moving at this point may change its direction. So due to polarization, some charges accumulates here. If you place a positive charge here, some minus charges accumulates here. So that produces external other field lines, so that the field present inside the dielectric may be different. So in such situations, we have to find out the electric field at different regions, what happens to the electric field when it crosses the boundary. Based on these two equations, they are called the tangential component of electric field and the normal component of electric flux. So any electric field coming into the boundary, suppose this is a boundary and it is moving like this, that is the second medium is more denser and then the first medium, that is bends towards like that. This is the first medium and this is the second medium. Then what we are actually doing is this incoming electric field will divide into two components, and one component is called the normal component En, or dN, and this is called ET or dt. Usually we are interested or usually take it as ET, and here it is dN because the normal component changes with respect to some sources. So anyway, so what happens to the normal component and what happens to the tangential component? That is what we identify in the case of this medium change. So this is called boundary conditions. So we'll explain this boundary condition in detail in the coming videos. So the two helping tools, once again, the two helping tools, one is the potential formulation associated, that is in order to simplify the problems with the source, and the other one is the boundary condition problem, that is in order to solve or simplify the problems related to the dielectric contrast, dielectric changes. Now before concluding, I would like to summarize what we have discussed so far. See, the electrostatic problem may be considered as a cause and effect principle, with the cause as the source, static charge, and the rho is the generalized form of the static charge and is the electric field. And we have two fundamental equations. One is Coulomb's law and Gauss-Flux theorem is the second one. We have the integral form of Gauss-Flux theorem here, and we also represent it as del dot T equals rho by epsilon 0, that is called the differential form of point form. And one more important equation we have to study, that is line integral E dot dl, that is conservative in nature, and we get del cross E is equal to 0. Then we have the potential formulation and boundary conditions as helping tool. So we get two relations, E is equal to minus del V, and the boundary conditions, the tangential component is continuous and the normal component is discontinuous by the charge density rho. Et1 equals Et2 means it is the same. There is no change when the electric field crossing the boundary if it is tangential, whereas the normal component, there is a change for the normal component, that is dN1 minus dN2 is equal to surface charge density.
So we have discussed about the basics of electrostatics, starting from the cause-effect principle, the aim behind electrostatics, and the basic principles and equations related to the evaluation of electric field and the conservative nature of electrostatic field, and the helping tools such as potential formulation and boundary value problems. The next video, I will give you the basics of magnetostatics. Thank you for watching.